Hello and welcome again. This week we're going to take a look at inputs to modules and, more importantly, sensors are most of what our inputs to a module would be. Our communication network is definitely an input as well, and every once in a while we'll get signals from other modules standalone that act as inputs. We're going to hold that off for next week when we talk about multiplexing and communication networks. But I really just want to take a look at sensors and make it so you have a really clear understanding of how these circuits are wired. They're very, very simplistic, and some of them are the backbone to how diagnostic trouble codes are created. So I find it really fascinating. I find it really important, and once you get the hang of it, then things become pretty easy. So let's hop right into it. What type of circuit do we have here? I've got on A, I've got a control switch. B is a module. C is very important. That's a resistor that is going to make it so that my voltmeter, that little circle there, has something to separate its power side lead from its ground side lead, so the red lead from the common or black lead. And then D is a set of lamps that power side switch, gave away the answer, that the power side switch is controlling. So this is a power side switch because it is on the voltage supply side of the lamps. You can see that there. Here's my voltage source coming in. The switch controls current on that power side before the voltage is dropped. And then we come down and here's the ground side. A little bit more complicated concept here. What will the voltage reading be with the module's internal voltmeter, the little circle, connected as shown when the external input switch is open or closed? So when switch A is open, what will we see for voltage? When it's closed, what will we see for voltage? And the key takeaway here is this voltmeter is sensing battery ground, chassis ground, and this meter lead is sensing whether or not voltage is present at that point. So if we take a look at it that way, it gets a little simpler. When the switch is open, we're not connected to voltage, so we have none. When the switch is closed, we have 12 volts because that's our voltage that the vehicle's battery is meant to work with. What type of signal does this produce? There's a lot of information to unpack here. Digital versus analog. So digital is just on, off, 1, 0. So switches tend to produce that type of a signal because a switch is all or nothing. It's either on or it's off. Analog sensors would be something that measures temperature, pressure, movement, and so there could be multiple different temperatures that the engine's coolant could be at, that the inside of the car could be. There are many positions that a power seat could be in, that a throttle plate could be moved to. Alright, so those are analog. And then the difference between DC and AC is direct current and alternating current. Direct current is what a battery produces, is what computers and modules want to work with. And it just means that the electron leaves the power source and travels in one direction until it reaches ground, which actually is the return to that power source, just on the negative side. Alternating current is what we find in the walls. So that means our electrons are moving back and forth, like what's happening inside of the alternator in the vehicle. This is not used for, I'd say, 99% of the circuits on a vehicle. Obviously the charging system uses it a little bit, and we'll see that some speed sensors will use that type of a current flow, but for the most part that all has to be regulated so that the computer can make sense of it. And so for this system where we have a switch and it's just hooked up to a battery, nothing crazy is happening, we have digital DC. When that's graphed out, it looks like this. So we have 0 volts in the middle, so we're staying on the positive side of that 0 volt line, which means that our current's flowing in one direction, which is what we want. If we come down here to the negative side, it means current flow is reversed. And it's just like when we switch the polarity on a motor. One way, the motor spins one way, the other way, the motor spins the opposite direction. So that would be a reverse in polarity there, which we do not get with a switch. And it's digital because it is either on or it's off. Now this is alluding to an oscilloscope graph. And what these boxes mean are, when we use an oscilloscope, and you'll get to see me do that next week, when we use an oscilloscope, we can make a choice as to what graduation these lines mean. So this could be 5 volts, and another 5 volts would give me 10 volts. And then on the bottom, I have my sweep, which is time frame. So this could be 1 second, another second, so 2 seconds, then up to 3, 4, or it could be milliseconds, so 0.001 second, 0.002 seconds. There's a wide range of choices that's available when we do that. Just a little information to whet your palate, so that next week you'll have a little bit of something to come into oscilloscopes with. Identify the power side switch inputs. So you can see all these switches down at the bottom are connected to ground. The ones in the module all seem to be connected to ground and ground and ground. I know it's pretty small there. But the only switch that has a power side connection is the main light switch, seeing as this is a generic electronic function module, generic electronic module. The module would be like a body control module, so it's in charge of lighting and comfort and information and entertainment for the customer. So that main light switch is a input that comes in and lets this module know that, hey, the lights have been turned off, or they've been turned on, or they're in the marker light position, or in the auto lamp position. So the module gives us all those different functionalities. Now this will be our next circuit that we deal with. We've got a switch at A, the module is B, C is our fixed resistor inside the module. Now this is called a fixed resistor because it's just a normal resistor. The resistance value does not change. And you'll see how that comes into play when we get into some more interesting sensor types. A switch is the most basic form of a sensor. Do we want it to happen, or do we want it not to happen? That's what the switch is there for. So it's still an input, it's still providing information, but the information is limited to a binary, one state or another state, 1 or 0, on or off. What type of switch is used? So is this power side or ground side? Take a look at where the power supply is, where the load of the circuit is, and if we pay attention, the load is the resistor at point C. That's the only resistance. And the switch is on the ground side of that load. See how we're closer to the ground? The resistance is the barrier between the ground side and the power side of one of these circuits. So this would be a ground side switch. Ground side switches tend to be the preferred method because if it shorts to ground, nothing's going to get fried. We have a resistor that can limit the current flow, so if I shorted to ground here, the same amount of current would flow through this circuit as if I just closed the switch and allowed it to find its natural pathway to ground. So this circuit is pretty robust. We're not worried about it hurting itself. The issue with a circuit like this, though, is a lack of information. We can only be told whether something is supposed to happen or not happen, and that's great if I want my horn to honk or my headlights to turn on, but it doesn't really help me very much if I need to know what temperature is the passenger compartment so that my HVAC controls can make the little mode door inside the plenum chamber in the dashboard. Does it need to move towards the hotter side or towards the colder side? What's the temperature of engine coolant? What's the temperature of the air coming into the engine? You get the idea. What position is the seat in? What position are the mirrors in when you get into memory seats and fun stuff like that. So then we have our switch again. What will the voltage reading be with the module's internal voltmeter? So the little circle connected as shown. So when the switch is open, what will we get for a voltage? What would that see? When the switch is closed, what would we get for a voltage? Now this is a part where a lot of you are like, I think I've got a pretty good idea of this. But some of you might be surprised to see that when the switch is open, we actually have 12 volts. Yes, we're sensing on the ground side of that resistor. So this would be my red meter lead here. This is my common black meter lead going towards ground. So yes, we are on the ground side of that resistor, and when current's flowing, that resistor would drop all of the voltage or pressure that's in that circuit. But the issue is that the switch is open. So when the switch is open, no current flows. And if we think to Ohm's law, to solve for voltage, I need to multiply amperage and resistance. And I don't know what the resistance value of that resistor is. Oftentimes they're somewhere in the range of 10,000 ohms. And the point of that is to limit current flow so that we're not wasting current from the battery and having to spend fuel energy and rob horsepower from our engine to charge the battery back up. But when no current flows, so let's say it's 10,000, 0 times 10,000 ohms is still 0. So what that means is no voltage is dropping. No current flow, we can't get a pressure differential between the power side and ground side of my resistor, because this is a restriction in the circuit. There's nothing flowing through it. There's no restriction to create a pressure differential, no pressure drops. So when no current flows, the takeaway is when no current flows, no voltage drops. So we're still able to sense available voltage, and now with that switch open, it's actually making a incredibly high resistance between my power side and my ground side of my meter leads. So that's why it's sensing two different things. When the switch closes, this meter lead is touching ground, and this one is touching ground. And remember that our meter is just measuring a difference between the two spots, the red lead and the black lead. So if they're both touching on ground, there's no difference. So we see 0, and that's what's displayed. No difference, 0 difference, 0 volts, because voltage means a difference, a potential. Ground side switch inputs. So that's an interesting one, because these are outputs, really. We're controlling ground of these lamps. These would be output drivers. They call the little transistors or relays inside the module drivers, because they're driving the circuit, controlling how it works. So the only inputs are down here on the bottom. These are door jar switches and a safety belt switch, so it would output through one of these switches up here, probably make the door jar light come on the instrument cluster, make the little beep go off and the light flash on the instrument cluster if you're driving around without your seatbelt switched. You can see how this module would need to take in a bunch of information to know whether or not that needs to happen. Is my seatbelt buckled? Well, does that matter if I'm not driving down the road? Does that matter if the key's just in the on position but the engine's not running? So you see, it might need to get information like, is the engine running? What's crankshaft RPM? Are we going down the road? What's the wheel speed? So it can calculate, oh, we're up above 5 miles per hour, so now I'll start bugging the customer. If they just wanted to scooch their vehicle around in the driveway, maybe we'll let them do that without bugging them too much. Now we get into something a little bit more complicated, but this is, in short, and in a very small view, what a module is built to do. I have my input side. Here's my switch. I have my processing and measurement. So my input is measured by the voltmeter. The processing is done by the CPU, so it takes that information and compares it to its programming. So here's our lookup table that tells me if I have more than 3 volts, greater than 3 volts, then I don't want my output to work. So these lights would not light up. If I have less than 3 volts measured by my voltmeter, then I want my lights to light up. So it controls our transistor by sending a current to the base in the middle there. See how it's an NPN. That would allow current to flow through our relays coil, creating electromagnetism that allows my bulbs to light up. So let's see what they have in store for us. With the module, will the module turn the lamp on or off when it sees the following input signals? So take a second. Pay attention to when that switch is open, what's my voltage going to be? Think back to the previous slides. When it's closed, what's my voltage going to be? Take a look at the lookup table. Is my voltage greater than 3? Now what we're going to see is either 12 or 0. They're just using 3 as a number that computers actually pay attention to. Depending on the processor, it could be a none of them can handle 12 volts directly. It has to be regulated somehow. But computers can deal with 5 volts, they can deal with 3 volts, 1.5 volts, 1 volt. So that's where this 3 volt comes from. Alright, you could pause me or we're just going to get on with it. But when it's open, when that switch is open, the output's going to be off. Which kind of makes sense, right? I don't want it on, I got the switch off right now, right? When it's closed, it's on. Now let's actually work through the nuts and bolts of this. So when that switch is open, current does not flow. So let's call that our 10,000 ohm resistor again. So to solve for voltage, how much voltage is dropped there, I would need to multiply current, which is 0 amps, times resistance, which is 10,000, but 0 times a bajillion is still 0. And so no voltage is dropped, which means I still have my 12 volt battery voltage, or maybe even 14 volts if the car is running. So that is greater than 3, right? The voltmeter would measure that, see it is greater than 3, and it makes the decision output off. Nothing is supplied to the base, power nor ground, and because of that, no current flows, no switching happens, and our bulbs are just chilling out there like it's any other day. When this switch closes, then current will be allowed to flow, and for 10,000 ohms, I want to say it's 9 milliamps. No, that would be for 9 volts though. So it must be 12 milliamps. So you can check me. So 0.012. Those of you with a phone handy will be able to tell me I'm a big old dummy real quick. But 0.012 volts or 0.012 amps would flow through this circuit if this is a 10,000 ohm resistor. So we'll do the math. 0.012 times 10,000. This is just zeros and moving some decimal points. Oh, 12 volts is dropped, is what that measurement tells me. So I used up 12 volts here. So I would measure 0 would be what's happened because this is the only resistor there. So we'll say my battery only has 12 volts to it. I would have to say yes, that is less than 3 volts. And so the output should turn on. The CPU sees that 0 volts. It looks at its programming and goes, oh, I'm supposed to do a thing. And it outputs a current, a voltage to the base, and which allows current to flow through my base, out the emitter, which allows a larger current to flow through the relay's coil, through the collector, through the emitter to ground, which creates electromagnetism, closes my switch, and the lights light up. Crazy, right? But this is exactly how a computer works. It takes input information, it uses its programming to determine an output. And this is just one circuit in there. Let's call this a door ajar switch. Is my door closed or is it open? So I would say that when my door is closed, the switch must open up, which makes it so I see the 12 volts there, and I don't need my interior lights to turn on. When I open the door, the switch closes, and the lights magically light up. But now we understand the process that goes through. And honestly, I mean, after we've done all this work, the only part of this that we don't fully understand at this point is the CPU. And we're going to play around with a couple different dual inline chips. We're not going to do any actual programming in this class because that's another big step. But these kits are meant to work with a device called an Arduino. They could also work with a Raspberry Pi, these are little processors, and the Raspberry Pi processor is what Android phones use, and obviously they're using a more sophisticated program, but the actual language, the programming language, and the way that the system works is a Raspberry Pi. So you can find this stuff on Amazon, and this summer, if we're still quarantined for the rest of eternity and you want to learn some stuff, there's a lot of good resources, and you have a lot of the devices you already need and a lot of the understanding you already need to be able to get into some programming. So long story short, we get the idea of how a computer works all of a sudden. Let's name the loads in the circuit. So these would be anything with resistance. So the coil has a resistance probably somewhere between 50 and 150 ohms, which is substantial for an electrical circuit. the lamps themselves, the resistors, these are all resistances in the circuit. Beep, boop. Are the relay contacts in this circuit acting as a power side switch or a ground side switch? You can pause me, but power side switch. They're on the power side of my lamps. Power side of the lamps, right? We should have that pretty quick. This guy over here, I think we have an idea what that's up to. Ground side switch. The output transistor, and they put in their driver. So this is my transistor, and this is what we consider a driver. You'll hear about coil driver circuits and all kinds of stuff like that. It's a transistor that's controlling the electrical circuit. So is the output transistor in this circuit acting as a power side switch or a ground side switch? Well, first we need to pay attention to what load we're controlling. It's this relay coil. And are we on the power side of it? Nope, we are on the ground side. And that's already given away by the fact that it's an NPN transistor. The N meaning that the N-type semiconductor material has to be on the ground side. It would otherwise be biased or reverse biased and would never flow current no matter what I provided to the base. Label the components in the diagram as direct or indirect outputs. Now, this is a concept that comes up a few times. It's whenever you're dealing with computers, but the basis of it is the computer controlling the current flow through the device? Like, is the current flowing through the computer? Or is the computer making something happen and then the current flow is flowing through a different circuit? That's the basis. So is the relay coil a direct input? Does the current flowing through the coil also flow through the module? It sure does. And the lamps are indirect because that direct output is causing something to happen. We're creating magnetism and it moves the switch, which then allows another output to actuate, which are the lamps themselves. But the current never flows through the module, which is probably for the best because the current flowing through those bulbs is probably a whole lot more, especially because they're in parallel, a whole lot more than what our little module, and especially that little transistor, could handle. That transistor is probably rated for a maximum of somewhere around 0.7 volts or 0.7 amps, and you know that that fuse is a 15 amp or 20 amp fuse for some bulbs, so there's no way that it would be able to work out for us. What will the available voltage be at the following locations with the input to the module in the open and closed positions? So we're looking at the collector first. The collector would just be, do I have power here when the relay is off? Do I have power there when the relay is on? And they just mean off is no currents flowing through there. Think about our little switch over here. This is just the same thing. It's a little switch. So and then the other one will be the normally open terminal, which is what the switch would move to when there's electromagnetism. So that one's a little bit simpler. But let's take a look. So with the relay off, no current flowing through it, we would not drop voltage. And right here at my collector, because this is an open switch, I would have 12 volts. Once the base is provided power, and this allows current to flow, so it's electrically closed, then current flows. This is the resistance, so it drops the voltage, and now I'd have 0. And this one's easy because it's just, am I connected to power when it's off? No. Am I connected to power when it's on? Yes, I am. So then I have 12 volts. That one's easier. All right, so now we're on to voltage divider circuits. This would be our thermistor, and a potentiometer would be the same way. Photoresistor would be the same way. And the concept here is they're dividing the voltage between the voltage dropped by two resistors. Here's a fixed resistor at point C. At point A, what they're pointing to is my thermistor. This is a variable resistor, commonly referred to as a varistor. Variable resistor, varistor. And then B is my module again. So the point here is that I have two resistors. Each of these is going to drop some voltage. Each one's a restriction. So I have 5 volts coming in. I have a restriction. It backs up some pressure. And as current flows through it, my pressure is reduced because I have a backup here and a little bit of relief on this end. And then it has another restriction, so there's still the ability to back up pressure between the thermistor and the fixed resistor, and then it goes to ground. This is called a fixed resistor because its resistance value is fixed at, let's call it 10,000 ohms of resistance. This is our variable resistor because depending on the temperature that it's exposed to, the resistance value of a thermistor changes, and that can be in two different ways. The amount of voltage dropped across each of these is completely based off of let me start that again. The amount of voltage dropped at each of these is based off of the amount of resistance in proportion to each other. So if this is a 10,000 ohm resistor and this is a 10,000 ohm resistor and I'm supplying 5 volts to them, this would drop 2.5 and this would drop 2.5, right? Each drops half because they're both the exact same resistance value. If this is a 10,000 ohm resistor because it's fixed and this drops down to, let's say, 2,000 ohms of resistance, then what we would end up having is, I'm not sure that this is 100% correct, but it's very close. We'd have somewhere in the realm of a 4 volt drop here. So if I took my meter and measured here and here, it would show me 4 volts. This meter here, because it's measuring the voltage drop across the thermistor itself, will measure that remaining volt of voltage to be dropped. The larger resistance will drop the majority of the voltage. But it doesn't matter if this goes down to 1 ohm of resistance and this is 10,000 ohms, this still will have, even though it's small, will still have a voltage drop because it is a resistance. Okay? So let's get on with it. There are two different types of thermistors, negative temperature coefficient, positive temperature coefficient. We've talked about this in previous labs, but the idea is a negative temperature coefficient means that as the temperature goes up, the resistance goes down. Positive temperature means that the resistance goes up as temperature increases. Oftentimes negative temperature coefficient thermistors are used, but PTC thermistors are used to protect devices. So let's say I have this output driver that's driving ground. There's no resistor, like here on these sensing circuits, to protect this. So if this switch closes and I have a short to ground, let's say the filament burns out and it melts the contacts and there's no resistance in that bulb anymore, this would be a short circuit and it would fry the tiny little transistor that's not set up for infinity amps of current flow through it. So what they do is they put this PTC thermistor device, and as we have a short circuit and too much current flows, it starts to heat up because excessive current flow is melting stuff. So as it heats up, the resistance increases and it limits the current flow and protects the device. And this is very common on lighting circuits for sure. All right. What type of signal does a thermistor produce? Actually, I want to go back a tiny little bit. All right, so this is the same circuit, but it looks actually like it would be in a vehicle. 12 volts comes in, and we have a voltage regulator. Now, the point of this voltage regulator is that for my sensed voltage, right, here's my voltage divider circuit, fixed resistor, variable thermistor there. What will happen is I'm measuring my voltage dropped across this device. So if my supplied voltage is changing all the time, right, I turn the key on, the vehicle's at 12.6, I crank the engine over. While it's cranking, the voltage drops down to 10 or almost 9.5 volts in some cases. And then I'm driving and my charging system kicks in and I'm up around 14.5 volts. Well, that move, like this could be sitting in 70-degree coolant, but the amount of voltage dropped across that thermistor will be different based off of the source voltage. So at 12 volts, it's going to drop less voltage than at a running 14 volts. And it's really important that we know the temperature of the coolant for emissions reasons and for combustion and fuel control and all that. So we need to know that 70 means 70. It doesn't mean somewhere between 65 and 80. No, it needs to actually mean 70 degrees. And so what they use are these devices that regulate the voltage. It'll step my dirty 12 volts down to a clean, perfect 5 volts. It stays at 5 volts all the time, always 5 volts. And that makes it so we can really trust the information that is supplied to the module and then used for its programming and output controls. It's incredibly important that we have this 5 volt regulator there to make sure that we have some sort of consistency there. All right, what type of signal does the thermistor produce? Is it digital or analog is the first question. Is it all or nothing, or is it variable? Well, it's variable, so analog. And then it's a direct current device because this is being supplied direct current, and all it's doing is limiting the current flow through it. It's not creating current, and nothing weird is happening, so no alternating current is produced. And here we go. It's cold outside. You start the vehicle up. The coolant temperature increases. It comes up to an operating temp, and then you shut the vehicle off and it slowly decreases back down to whatever ambient temperature is. What happens to the voltage as the thermistor's temperature increases? Now that depends on whether it's NTC or PTC, and most of the time sensors are going to be negative temperature coefficient. So the resistance goes down as the temperature goes up. So they're saying what happens as the temperature increases and resistance on that thermistor decreases. Take a second, think about it. Voltage will decrease. The largest resistance will use the majority of the voltage or drop the majority of the voltage. So if this is becoming a smaller resistance, it's going to use less of the voltage. Identify the thermistors. There you are. Not too hard. You can see what that arrow through the resistor just means is it's variable. So for a thermistor, they just use that. For photo ones and other devices, they add some other little bits and pieces to make it so that it's clear that it's not just for temperature. All right, look one more time. So long. On to potentiometers. Oh, and this is talking about the DC to DC converter, which I talked about for reference voltage. So on to potentiometers. So when we have a potentiometer, sometimes you'll see that they wire in a fixed resistor, and then technically this part's another fixed resistor because it doesn't change. And then other times they just limit how far the wiper can travel, like maybe it can't go all the way up and bypass the resistor and all the way down and hop off the resistor again. And it's not uncommon. The issues with this is that if we get a short circuit at a point like this, then we could fry the internal. So usually this is just a line drawing for simplicity, but usually there's a resistor built into the module to protect it. But long story short, the basic idea here is voltage pushes current through the circuit, and as the current travels through this resistor, voltage is dropped. Now it doesn't all drop immediately right there at the top. It drops over the entire length of the resistor. So they put this wiper sliding contact on the resistor, and what it would see at the top, let's say that there's no limit to travel, touches the wire before the resistor, 5 volts, and then as it travels down, 4.5, 4, 3.5, 3, 2.5, 2, 1.5, 1, 0. So I have a fixed resistor, but the point at which I'm measuring voltage is variable in this case. And this is used for position and pressure sensors. So if I want to know what the pressure in my AC line is, they put a pressure transducer in, and the pressure physically pushes up against a diaphragm, which then is attached to a wiper and moves it back and forth. Think about a throttle body and the throttle plate being moved by the throttle linkage and your foot depressing on the accelerator pedal, pulling on the cable, moving the linkage, or nowadays there's an electronic motor built in to move it. But that movement, the wiper is attached to the throttle plate, and as the plate moves, it moves the wiper across the resistor. Power seats have this. Power windows, especially with one-touch features, have this. Door locks are starting to have this built into them as well, so it can tell whether or not the door is locked, unlocked, or maybe even stuck and partially locked, which that's getting into like advanced safety stuff. What type of signal does a potentiometer use? So direct current, is it digital or analog? All or nothing or variable? Oh, it's variable. The same chart as what we saw before. You're at a stoplight, it's idling, throttle plate's a little bit open so the engine can breathe, but not enough so it really speeds up. You accelerate, come to a cruising speed, and then the next light turns red because that's how life is, and then you decelerate, engine slows down, and you're just chilling out, idling, waiting for it to happen. Where's the potentiometer? Boom, right down there on the bottom. And this would be definitely part of something like a what does that say? Remote climate control. Oh, okay, so this would probably be one of the mode or temperature doors inside the dash that makes it so that our blower controls work the way we want to. If I want it to be 80 degrees, then that motor that moves the door back and forth needs to have some sort of feedback to make it so it knows that it's actually in the right spot. Stepped resistors, and I talk about this in this week's lab as well. Stepped resistors make it so that, in this case, I've got 3 wires. Well, let's make this bigger. You can read the writing on your own later. But I've got 3 wires, and that's allowing for my multifunction switch. So this would be my wiper control switch. You know, which one of the multiple intermittents do I want? Do I want it just to wipe? Do I want it to go high? Do I want the washer to wash? It makes it so that with these 3 wires I can have 1, 2, 3, 4, 5, 6, 7 different intermittents from the looks of it. Yeah, minimum up to maximum, that would be 7. And then I get a high speed, a low speed, and a wash function out of it too. And because all these wires have to fit up through the column of the vehicle, of the steering system, the steering column, words are hard, because these wires have to make it all the way up there, and we have multiple controls, and this is also really common on the control buttons and stuff on your steering wheel. They want to use as few wires as possible. It's cheaper that way, but it also makes it so that the column can actually be compact instead of having a wiring harness that's this big coming through it, because we want 2 wires for every one of our switches. It's not possible. So this makes it, with all these different resistance values, we just get slightly different voltages in the module, and it looks at its programming and can tell, oh, between 1.5 and 2 volts, that means I want intermittent 4, so it controls intermittent 4. Pretty simplistic, eh? Make it small. Make it go. What type of signal does a stepped resistor produce? So this one's a little bit tougher because it is switches. So the switch is all or nothing, but the reality is one switch doesn't bring us to the maximum voltage, and the next switch brings us down to the minimum. There's a tiered, like a staircase, notchiness of it. So it's direct current, but it's analog. So this image is not excellent, but it would look more like a staircase as we go through the different ones. And it doesn't necessarily go in a descending order. It may look all crazy, like a landscape looking at mountain line or something like that. A keypad switch is another way of creating this stepped resistor type of feature, except for instead of it being variable voltages on each one of these lines, when a switch closes, it's either going to allow current to flow and change in this case we use a 12 volt reference, which would still be regulated, but it drops my voltage when the switch gives me a pathway to ground, and does not when, let's say, I close this switch. Can I get to it? Oh, I still can. Well, we'll close number 5 then. I close number 5. Oh, diode stops me, so in this case I'd have 12. When 2 is closed, I would have 0 because of the availability of current flow. What these switches do is, this would be a keypad on a Ford, so you push the key code in, you punch the key code in and it unlocks the doors. You hit a couple buttons and it locks all the doors for you. And so each one of these switches is given a different functionality. And that functionality is it the 1, 2 button, the 3, 4, 5, 6, 7, 8, 9, 0 buttons. So that means each button is, you push the same button for 1 as you would for 2. And that's all that's going on there. What type of switch are these? Well, if you pay attention, they're on the ground side.